Hello students, welcome to the second session on Lebesgue measurable functions. In our last session, we discussed about the definition of a Lebesgue measurable function. We also discussed two important results that first was a constant function defined on a measurable domain is always measurable. Secondly, we discussed a continuous function defined on a measurable domain is always measurable. We also verified that the converse of this result need not be true. Today we are moving forward and we will be discussing two important results. First one is, the first result is, if f be a function defined from E to R, where E is a measurable subset of R, and if f from E to R, where E is measurable, be a measurable function then mod f is also measurable. So discuss its converse also. Discuss its converse. Okay. So now let us verify it. So if we are given f is given to be a measurable function, we want to prove that mod f is also measurable. So solution is like this. So we are given that what is given, f from E to R is a measurable function. So now we want to verify if mod f is measurable, right? So let alpha be any real number. So if we have to prove that some function is measurable, then for that function, we want to check a corresponding set is measurable or not. So we are going to consider that set. So now consider the set. Consider the set. Let us call it A. So that is A's set of all those points of E for which mod f of x is strictly greater than alpha. This is by our definition. So I can further write it as A can be written as all those points in E for which mod f of x is strictly greater than alpha. Okay, now it all depends upon alpha. If we want to proceed further, we have to look at, since alpha is given to be a real number, right? So now it is possible that alpha can be positive, alpha can be negative, as well as alpha can be zero, right? So now there is one obvious case, because we know that the mod of a function is always non-negative. So in case we consider the case that alpha is negative, in that case, so irrespective of the value of fx, mod fx is always going to be non-negative. So if alpha is negative, mod fx is going to be non-negative. So it is always strictly greater than alpha for every xn. So I can write this as, so one case follows very easily. That is, in case if I write, if my alpha is negative, if I take alpha to be negative, in that case, every point x in E will satisfy this condition. So this is my, because we know mod of a function is always non-negative. So if we take alpha to be negative, it is always going to be non-negative. Now second case is in case my alpha is positive or zero. So I'm going to combine this case. So secondly, I'm going to take if alpha is non-negative. So what will happen? So you must remember one thing. If we have mod x is greater than alpha, then what values of x will satisfy this? So for this, I can write, so mod x is strictly greater than alpha, where alpha is a real number, if and only if x is greater than alpha or x is less than minus alpha. So here we want mod fx to be greater than alpha, and alpha is positive, right? Non-negative. Alpha is positive or zero. So this case corresponding to alpha non-negative, I can write it as all those x in E for which fx is strictly greater than alpha, union all those x in E for which fx is strictly less than minus alpha. Now, this set for alpha non-negative has been decomposed into union of two sets that are represented in terms of f of x. And we know that my function f is measurable. Now, we want to see whether this set, now my mod f is measurable if this set A is measurable. Now look at what is my A. So if alpha is negative, in that case, my set A is E. And if alpha is non-negative, so then my set A is union of these two sets. Now, we will look at it one by one. So we are given in the definition, when the hypothesis, we are given that the function f is defined on a measurable set. So E is given to be a measurable set. So since E is given to be a measurable set, so when alpha is negative, in that case, A is coming out to be E. So E is given to be measurable. Secondly, if alpha is non-negative, in that case, my set A is union of these two sets. Now, if you look at the first set, it is all those points x in E for which fx is strictly greater than alpha. Since f is given to be measurable, so this set is measurable. And secondly, uh, the second set is x in E for which fx is strictly less than minus alpha, right? And we know our function f is measurable. So for every real number, this set is also measurable. And we know that finite union of measurable sets is measurable. So as a whole, both of union of these two is going to be measurable. So therefore, I can say in both the cases, E is measurable and this set is also measurable. This means I can say my set A is measurable. A is measurable. So since my set A is measurable, so this means I can say the function mod f is measurable. So this way we have proved if f is measurable, then mod f is also measurable. Next, we want to look at its converse. So its converse is if mod f is measurable, we want to see if f is measurable, right? So the converse in this case is not true. Means if f is measurable, it is not necessary. This does not imply f is measurable. We will prove it also. So how to prove it? That if f is given, mod f is given to be measurable, we want to show f need not be measurable. We will prove it now. So let P be a non-measurable subset of semi-open interval 0, 1, right? So now define a function. We call this set to be E, say, right? Okay. So now define a function. Define a function f from E to. So E means this semi-open interval 0 to 1. E to R as. How we are defining it? So f of x is 1 if x is coming from P, if x belongs to P, and its value is -1 if x does not belong to P, right? So this is how I have defined my function fx. So now consider the set. X in E such that fx is greater than 0. Means we are considering this case for alpha 0 in real numbers, right? So because if a function is measurable, then the set that we consider, then the set for if function is measurable, then for any alpha in R, x in E such that fx is strictly greater than alpha should be measurable. So in this case, what we have done, we are considering this case for alpha equal to 0 because it should be valid for every possible real number, right? So I have considered the set x in E such that fx is positive. Now, if you see the definition of the function f from E to R, its value is 1 when x belongs to P. Its value is 1 when x belongs to P. And we want the function to be positive. So when function is positive, when its value is coming out to be equal to 1. And when its value is 1, then it will satisfy the condition fx is strictly positive. So which is this set? This is the set when x belongs to P. So I can write, so this is equal to, this set is P. This is equal to P, which is non-measurable, which is non-measurable. So therefore, this condition is not satisfied for each real number. This is failed for alpha equal to 0. So therefore, I can say, since the set is not measurable, so therefore, f is not a measurable function. Okay, so f is non-measurable. F is non-measurable function. Next, we want to show mod f is measurable. Okay. On the other hand, what about what about mod f of x? So this is nothing but mod f of x, right? So its value is 1 for every x belonging to E. Okay, so this means what we can say. So it means mod f is 1 for each point in the domain. So this means mod f is a constant function. Is a constant function defined on E. In previous lecture, we have proved that every constant function defined on a measurable set is measurable, right? And E is given to be, E is nothing but 0, 1, semi-open interval. So this is measurable, right? So this means mod f is measurable. Why so? Because every constant function, every constant function defined on a measurable set is measurable. So in this way, we have seen if a function is measurable, then its mod is always measurable, but the converse is not